Welcome back! I am so incredibly excited for today's explainer because we're looking at the mathematical engine that drives the universe's most explosive changes. Whether we're talking about populations of bacteria doubling in a petri dish, radioactive materials decaying over millennia, or the way a viral trend suddenly takes over the internet, we are talking about one specific mathematical concept. Today we're exploring exponential functions, the math of rapid growth. We're going to dive into the mathematical definitions and graphs straight from our source material to truly understand how these functions work, what they look like, and why they are absolutely the undisputed rock stars of calculus.
Let's kick things off with Section 1, Introduction, from polynomials to exponentials.
To really appreciate why exponentials are so special, we first need to look at what they aren't. In our earlier explainers, and throughout basic algebra, we looked at power functions like x squared, where the base changes and the power is fixed. But today, we flip the script. We are taking that familiar power function and physically swapping the base and the exponent to create something entirely new.
Welcome to exponential functions. Here, the base is a constant a, and the variable is the exponent. It sounds so simple, right? Just moving a letter up a tiny bit. But this small change creates the most powerful growth patterns in nature, from spreading viruses to growing bank accounts. When the variable climbs up into the exponent, the function grows far more rapidly than any traditional power function ever could.
Moving right along to Section 2, the rules of the base.
Now that we have our new function, we have to establish the ground rules for that constant base a, and the rules are strict. The base a must be positive. Why? Well, think about it. If a were a negative number, raising it to a fractional exponent like 1/2 would mean taking the square root of a negative number, and that instantly kicks us out of the real numbers entirely. Also, if a equals 1, the function is just 1 to the power of x, which is just a flat line. But when a is anything else positive, magic happens.
To actually use these functions, we also rely on these 4 laws of exponents to simplify complex expressions. You can see how multiplying matching bases means adding the exponents, division leads to subtraction, a power to a power multiplies them, and how a power perfectly distributes. These are the fundamental tools you'll use throughout your calculus journey, so you definitely want to lock these into your memory right now.
All right, let's look at Section 3, Growth versus Decay, the visual story.
So, we have the algebraic rules down, but what do these actually look like? Look at these shapes. If the base a is greater than 1, the function explodes upward. This is exponential growth. It perfectly models things like unchecked population surges. But on the flip side, if a is between 0 and 1, it represents exponential decay. The curve starts high and decreases downward rapidly, which is exactly how radioactive isotopes break down.
What's really fascinating here is the visual anchor tying everything together. Notice that all these graphs pass through the point 0, 1 because any positive number to the power of 0 is 1. It provides you with this perfect, reliable mental anchor right on the y-axis, no matter how wildly different the curves might be.
Also, notice how they flatten out at the bottom? They never actually touch the x-axis, it's their horizontal asymptote. The lines will get infinitely close to 0, but no matter how far you zoom in, they will just hover infinitely close to that invisible boundary without ever crossing it.
Which brings us to Section 4, the star of calculus, the number e.
In the world of calculus, not all bases are created equal. The crucial point is figuring out the slope of the tangent line right at our anchor point of 0, 1. If we use a base of 2, the slope is about 0.7. It's a bit too shallow. If we bump the base up to 3, the slope is about 1.1, just a bit too steep. Mathematicians looked at this and thought, isn't there a base perfectly in between that gives us a slope of exactly 1?
And there absolutely is. Of all possible bases, one is truly special, the number e, approximately 2.71828. Going on forever without repeating, kind of like pi. It sits perfectly between 2 and 3, and it is arguably the single most important number in all of higher mathematics.
So, why e? Because it's the only base where the slope of the curve at 0, 1 is exactly 1. This makes your life much easier in calculus when we start calculating derivatives. It literally means the rate of change is perfectly proportional to the function itself. We call f of x equals e to the x the natural exponential function, and it is the undisputed king of calculus operations.
And finally, Section 5, Conclusion and the Paperful Challenge.
We've covered a ton of theory today, but let's bring it crashing back into the real world. Here is a mind-blowing challenge. If you take a standard piece of paper and fold it in half 50 times, each fold doubles its thickness, creating an exponential function. 2 to the power of n. How thick do you think it becomes? Is it as tall as a building, a mountain, or something else? Guess in the comments.
Need a hint? The answer involves a distance to the moon. I know, it sounds literally impossible, but that's the point. Exponential functions totally sneak up on you, and their sheer power is absolutely staggering. Well, that wraps up our explainer. Next time, we explore the undo button of exponentials, logarithms. You won't want to miss it. See you then.